Hello, hello, mic check, mic check, mic check. Is that coming through? Oh, that's bad news. Nobody's saying they can hear me. All good? Thank you. I'll see you in 9 minutes. Okay, everyone, you should be seeing my desktop round about now. That's kind of disconcerting. Okay, so this evening's lesson, what we're going to take a look at is the equations on the left hand side of your screen. Okay, so that's work done, power, potential energy, and kinetic energy. So we're going to start with the concept of work done. So if I take an object, right, any object at all, so there's a little box, and I want to move that object, from here over to somewhere else. So let's put a little dotty arrow. I want to take this object and move it over here, okay, so that it ends up there. Shorten that arrow a little bit. Then that's going to require a force to do that. Okay, so some size of force F is going to be required in order to make that happen. So we'll stick a little F in there. Okay, now how long I have to apply that force for depends, of course, on the heaviness of the object, how much friction there is going on, all that type of stuff. But at the minute we'll just call it F, and we're going to move it a distance d. Now it turns out the total amount of energy that I have to expend in terms of getting it from A to B is the work done. Okay, so work done is the energy used when you produce a force and that force moves an object a distance. Okay, so work done, which is an energy and therefore measured in joules. Yeah, it's a terminology difficulty there, because work is something that you imagine you do at a table or you go to work. Okay, work is technically an amount of energy you do, and it is equal to the force applied multiplied by the distance moved. Now for those of you in triple award, it's the distance moved in the direction of the force. Okay, not a big deal. It's pretty much the same thing. Provided the force and the distance travelled are in the same direction, you can kind of ignore that bit. But sometimes you have forces that act at a slightly different angle, so then you've got to do some interesting trigonometry on that. Was that alright, everybody? Following? Happy? Right, good. Hoping it's happy. I'm 5 seconds behind, so we're all okay? Nice one. Okay, so that's our first equation. Okay, so kind of top left of the screen here, we have work equals force done, force applied times distance moved. Okay, now work done is synonymous with another thing. Now, if I'm an examiner, I don't set you this question. Okay, what I do is I change work done and I change it to energy transferred. Okay, so if energy is transferred, oh dear me, good help if I, no, that's okay. If energy is transferred from one place to another, work has to be done. So if I turn kinetic energy, for example, into potential energy, then work is done. If I turn heat energy into sound energy somehow, work is done. Okay, and the amount of energy that's transferred from one type to the other is the amount of work. Okay, happy enough? Thanks very much for the comment on streaming full time. I think I'll calm myself on that one. If I get through the next 30 minutes, I'll be absolutely delighted. So we're 5 minutes in-ish. I just want to check that my timers are running, because I don't want to keep you any longer than 30 minutes. Okay, so stream timer's running. You can't see it, but it's running on my secondary desktop. Right, on we go then. So that's work done. And generally speaking, just drops into that. Now, if you are somewhat maths phobic, and that is that you are good at maths, you just think you're not, right? Because there's nobody that goes to our school or nobody that watches this channel that's bad at maths, right? It's just a fact. Okay, you might think you're bad at maths, but you're just not. We have this little memory triangle where we have work done at the top, we have force down here, and we have distance moved over here. Happy enough? So if I want to create an equation for this, if I want to say if I've been given the work done and I want to find the force, then I cover up, and this could be interesting, with no whiteboard to play with, so I'll make a little circle and I'll fill it in. Okay. So if I want to find force, then I cover up the F and I'm left with WD over D. Okay, so the force applied then is going to equal the work done divided by the distance travelled. Happy enough? Okay, cool. If I want to find the distance travelled, again I just cover that up, and that gives me work done. I'm going to go back to my black font because that red one's a bit annoying. That gives me that the distance travelled is equal to the work done divided by the force. Now, to be honest with you, you guys are all sufficiently good at math that you're probably able to work that out from the original equation. But be aware, if you really don't like maths and you're in an exam, this triangle does not count as the formula part of your equation. Okay, it doesn't count until you have an equal sign. So only when you have it as these things do you actually get to say that's my equation mark. Happy? Alright, cool. So that's work done. We're going to move on a little bit because we've got some questions and stuff for us to try a little bit later on. Okay, so on our next page then, we have our second equation down, which is anybody who's in my class knows that this is the unpronounceable word for Irish people, and that is power, or power, or whatever. And power is how quickly you can do work. Not quickly is the wrong word, but the rate at which you do work, and it's measured in watts. Okay, so W for watts, and it's the rate at which you can get work out. How many joules of work you can do per second is your power. Okay, so if I have 500 watts of power, that means I'm putting out 500 joules of energy every second. I'm doing 500 joules of work in 1 second, 1,000 joules of work in 2 seconds, 1,500 joules of work in 3 seconds, and so forth. It runs up, it runs up, it runs up. Okay, so power is work done divided by the time taken to do that work. Right, and this software is amazing, but really bad at fractions. Right, disturbingly bad at fractions. Okay, work done over time. But remember, again, unkind examiner is going to go, wait a minute, we're not going to do work done, we're almost certainly going to do energy transferred again in here. Right, so think, so pop energy transferred in there. Sorry for the really clicky keyboard. So let's think about something being pushed up a hill, for example. Right, so if I have a little slope here and I want to send something up that slope. Alright, so I might send it on to the bottom of the slope, and I'm going to send it on with I don't know, 1,000 joules of kinetic energy. So that's E subscript K. Subscript would be useful. Okay, so 1,000 joules of kinetic energy, and away it goes up a hill. Okay, until it runs out of energy. Okay, well, when it gets to the top of the energy, it's run out of kinetic energy, so it's not moving anymore. But all that energy has been transferred into potential energy, so it goes to from 1,000 joules of EK to 1,000 joules of EP. Right. So how much energy was transferred? 1,000 joules was transferred from kinetic into potential, so that was my work done. 1,000 joules of work was done, time taken, however long it took to get up that hill, and I can measure the power. Happy? Good. Okay. The real Mr. Smith in chat. Yeah, we'll work out who that is. We'll work out who that is at some point. Okay. Good to see you, Ryan. Interesting use of kind of, well, I'm not quite sure what that is, Hebrew text or something. Interesting. Alright, good. Okay, so that's our top two equations done. And again, this one lends itself to a little memory triangle as far as the math goes. A little bit different on this one though, that the object that you're looking for is in the bottom corner. Okay, so power is down here with work done up in the top here with work done there, and time taken over here. But again, it's the same principle. If you want to find out one of them, you cover up the one that you're looking to find, and that leaves you with the equation you need. So if I'm looking for power, I'm left with work done over time. Time is work done over power, and work done is power multiplied by time. Okay, Ryan, you're desperate for a shout out. You got a shout out. Okay. And cans, I won't be playing some. Well, I might play some CS, but I'll certainly not be doing it on stream. My computer would explode. But if anybody wants to drop me £1,000, to get a gaming rig, I'm good with that. All right, on we go. On we go. Oh dear, Adam, if I start doing shout outs for everybody, I'll just go through the now 60 people watching and shout them all out at once. But there you go. There's your shout out. See what I mean? All right, next one then. We have our two kind of equations on energy, which is the potential energy equation. So EP is equal to mgh. Now that's the straightforward one where we have to now define these terms. Okay, so it's an energy, so this has to be potential energy. The word energy appears, so it has to be measured in joules. No excuses, no nothing in that. Okay, it can't be anything other than joules. Because it's joules, all these other things must be measured in the correct unit. So mass, m, height, h, and gravitational field strength, g, all have to have the correct unit. So this is mass, and it must be measured in kilograms. If you don't measure it in kilograms, you don't get the energy in joules. That's your problem. Okay, this has to be gravitational field strength. And gravitational takes too long to write, and that has to be measured in meters per second squared. Okay, because gravitational field strength is the acceleration due to gravity. And then finally, my height has to be measured in meters. So all my standard units. So again, if you're in an exam situation, the very obvious thing to do if you're an examiner is to give you heights in centimeters, give you masses in grams or tons or weird things like that. Happy? Okay. This one lends itself to a triangle, though it's a little bit more awkward because it's got a three-layer base to it, which gives you M, G, and H across the bottom, with E subscript P up at the top. Now, if there are any of my first year maths class watching, I hope you're really understanding why I bothered to spend so long on algebra with you, because you can see that the year 11 course is just lots and lots of letters. Okay, so it's like that. And once again, the covering up system works, but you end up with a couple of things on your bottom line sometimes. So this one would be cover that up. If I want to find the mass, it's going to be EP over GH, where G is multiplied by H before anything else happens. And then H over here is EP over mg, and again EP is mgh. No problem at all. Okay. Mr. Smith doesn't need a pay rise, you're absolutely right about that. But yeah, it's a privilege to teach you lot. Alright, good with that. Now, that's our third. We're on to our final equation now. 16 minutes left on the clock in terms of how long we've got with you. The equations are not the bit I want to talk to you about, so I'm going to try and get through this quite quickly. Leaves us with EK, the kinetic energy. This is an object is moving, it has to have kinetic energy, is equal to a half. Now that should be written as a fraction, but this package sucks at fractions, so we're not going to do that. So that's a half. That's 1 over 2. The mass times the velocity squared. Now, if you're in chat and you're a first year, what bit of this equation gets done first? Because we've covered this loads and loads and loads and loads and loads. I'm waiting. I'm still right. Which bit is it? Is it the half? Is it the m? Or is it the v squared gets done first? Poppy, I can see you. You don't half the m, not the first one. Okay. What about that? Andre McCarran, shocking altogether. Probably true right enough, but yeah, probably true. Okay. Bid mass, so we've got no brackets, but we do have an indice, so the velocity gets squared first. Okay. The velocity gets squared first. Do that first, then you can multiply it by m, you can multiply it by a half after that, but really be careful. It's just the velocity that gets squared. The most common mistake we see as examiners is that you do a half, you multiply it by m, you multiply it by v, and then you square the whole thing, which is just silly. Okay, it's just v squared then. Now, if you've got a real problem remembering that, stick it in brackets. Okay, you know it's not wrong. It's a bit weird, but you can do that. That's fine. And again, because this is an energy, this has to be measured in joules. You've got no choice in that. Okay, and because of the fact that you therefore have kind of committed yourself to joules, you must commit yourself to the correct units for each of these. So the mass has to be measured in kilograms. So mass in kilograms, and the velocity or speed, to be honest, because it doesn't matter, so it's velocity or speed, and that has to be measured in meters per second, and then when you square it, that unit becomes meters squared per second squared, if you really want to. Okay, we good? Hopefully that's alright. This leads to a triangle as well. It's basically the same process as the other ones. You stick the EK at the top, so what's on one side of your equal sign, because they're all together, and that gives you a half in the bottom corner, which is no use to anybody because you never want to find a half. M and v squared. Now, for those of you who really do struggle with maths, be careful with this, because this triangle does not give you v. if you're asked to find the speed of this object, this triangle does not give that to you. What it gives you is the speed squared. So once you go and find v, so let's just show you how that is. You go and find v squared. Okay, what you're covering up here is v squared, it's not v. So you do ek over a half m, that gets you v squared. Remember, you're going to have to square root that at the end to make yourself get a value of v. M's easy, it's ek over a half v squared, and ek is a half mv squared. And if you really fancy getting a half, the kinetic energy divided by the mass times the velocity squared will always give you 0.5. Happy? Good. All right. Try and keep the chat relatively clean. You never know who might be watching. You know, want to keep our PG rating. All right. Good. So, what's the point of all this? Well, the last two equations primarily are about working out what happens to stuff as it falls. So, if, for example, I have like ground level down here, so we'll make some ground. I want to get some filters in that. Let's give it a gradient fill. Everybody loves gradients, right? Okay, there you go. So we've got a nice gradient fill there, and I'm going to drop a ball from a certain height. Well, maybe not drop a ball, drop a reasonably heavy object. I'm going to drop it down that way. Okay, so let's say our ball has a mass equal to 2 kilograms, and it's going to fall a height of 5 meters, okay, up in the air. What I want to do is I want to find out how fast is it going when it hits the ground here. We want to say how fast at that point. So how fast as it hits the ground. Now obviously when it hits the ground, very shortly afterwards it's going to be stopped. But when it hits the ground it's definitely moving. That's why it hurts, it's why it makes a bang, it's why all this type of stuff happens. So in order to do that, we have to use something called the principle of conservation of energy, which says that energy cannot be created, it cannot be destroyed, but it can be changed from one form into another. Okay, and that in really short terms, really short mathematical terms, that just says that the total energy remains constant. The total energy remains constant. It can change, you know, kind of what type it is, but in total it remains constant. So up at the top here, we want to find the potential energy. So that's EP. That's okay. So get my subscript in. Yeah. Remember my keyboard shortcuts, and that equals mgh. Right, because we know we're off the ground, we're going to have potential energy. Right. So that's equal to our mass, which is 2 kilograms, times the gravitational field strength on Earth, which is 10, times the height that it is off the ground, which is 5 meters. Okay, all our units are okay. We're not being tricked by grams or centimeters or anything like that, because I'm a nice examiner and we're easing ourselves into it. Okay, so that's going to equal 2 times 10 is 20, times 5 is 100 joules. Easy stuff. Right. At the top here as well, we can calculate the kinetic energy because it's worthwhile doing. That's the type of energy it could have, and that's a half mv squared, which equals a half times the mass, which is 2, times 0, that's how fast it's going, squared. Okay, I don't really need the brackets, I just put 0 squared there. Okay, so a half times 2 is 1, multiplied by 0 squared is 0, which makes sense. It's not moving, it shouldn't have movement energy. Okay, so my total energy equals 100 joules. Easy. Right, now down at the bottom the situation changes, but we start with our total energy equals 100 joules. That has to be true because the principle of conservation of energy says that the total energy remains constant. At the bottom we've got E subscript P equals mgh. Okay, the mass again is 2, the acceleration due to gravity is 10, or the gravitational field strength is 10, we know that already, but its height now, its height off the ground is 0, which gives us 0 joules. Now you don't have to show that every time, you can just say it's on the ground, it's 0 joules. So that leaves me with EK equals a half mv squared. Okay, but I don't know what V is, I'm meant to be trying to find that out. But I do know that since the total energy is 100 joules here, and that the potential energy is 0 joules, then the kinetic energy must be, logically speaking, 100 joules. Okay, that's where all the energy's gone to. Energy's been transferred to there. So the energy equals 100 equals a half times m times v squared. So and then again we go and stick our numbers in. That's 100 equals a half multiplied by the mass, which was 2 times v squared. It's out quite nicely. So 100 equals a half times 2, 1 times v squared, which is just v squared. So to get v, we take the square root of both sides, and that gives me that v equals 10 meters per second when it hits the ground. Okay, now this is the likely question you get. Far of this. Okay, that's a bit harsh to say. You should already know this. That's why they're here. Okay, happy? Good. Okay, so get you onto something a little bit more tricky. We've got about 7 minutes left, so let's try a couple of pre-prepared questions. So I've sent you in the description below. You'll see a link to a Google Doc. Okay, and a Google Doc is these questions. So if you're on a computer, grab them. If you're not on a computer, you should be able to see it on screen at the moment. I'm not sure what the size is like, depending on your device. So a swimmer in a 100-meter race exerts an average force of 80 newtons to move through the water. Calculate the work done by the swimmer. So I'm going to give you 10 seconds to have a little think about how you're going to approach that. Then we'll do it on screen. Now, if you've got a piece of paper in front of you, you've got a pencil ready to go, work ahead of me. Work ahead of me and go for it. Okay, good. So we got 10 seconds of that. Okay, so this is a work done. So again, it's formula. Work done equals force times distance. That's 1 mark, straight up. You have no idea what to do after that, but I know this is a work done question. I've done my revision. I get my equation mark. Then it's work done equals, is there a force up here? Yeah, there is, 80 newtons up at the top. So 80 newtons is my force, multiplied by the distance moved, which is 100 meters. That's 1 mark. Okay, so the work done then finally is equal to 80 times 100, so that's 8,000. And it's a work done, so therefore it's an energy, and that's joules. And that's worth your 3rd mark. Now you might think that's super easy, but this question is from the sample assessment material for the new GCSE physics. Okay, and I'm not talking about double award physics. I'm talking this is a triple award question on their sample material. Okay, so there are questions that are straightforward, formula, working, answer, unit, and it needs to look like this because everybody can press the wrong button on a calculator. Okay, so make sure you score the easy marks. Right, good job. Okay, good work in Doomsday. That's nice. Good, good, good. All right, on we go. Next one then. The swim lasts for 40 seconds. This is our second equation, left hand side. Use your answer to part 1 to calculate the power of the swimmer. Include the unit for power in your answer, so we're going to get a 4th mark for this. So we've got our equation to start with. Left hand side of the screen, power is equal to work done over time. We're being asked for power, so we don't need to rearrange that. So straight up, we've got a mark. And again, I'm going to stop for about 10 seconds, let you guys run through that, see if you can get the thing. Okay, Llama, please mind the language in here. Okay, we can't be having that. All right, cool. So we're ahead and ready to go. Good. So this time the power, if I can get back to my screen, P is equal to the work done. That's our previous question answer, which was 8,000 joules, divided by the time taken, which is 40 seconds. So power is equal to 8,000 divided by 40, so that's 800 divided by 4, which is 200, and power is measured in watts. So you'll get a mark for the 200, and then you'll get a mark for the W. Happy? Good. Nothing to it. Nothing to it at all. Right. Next one then. Here we get a little bit more into things. Okay, so the graph shows how the gravitational potential energy of a stone changes as it falls. Okay, so on the grid, draw a graph to show the total energy of the stone during the 4 seconds of its fall. So I'll take you back to the page where we did that, and this is all about this one statement here that most people forget about because they're completely insistent on learning all their definitions and all their equations that they forget what's the purpose. Total energy remains constant. Right, so it doesn't change. So this is all very interesting about potential energy, but the total energy remains constant. So when you're drawing this line, you simply draw a line that it had 400 to start with, and therefore it continues to have 400. My mic's glitchy. Is it still bad? Oh dear, that's not so good. 299, one that I nicked from school. Let's see. Any better now? No? Yeah? Okay. Total energy remain at 400. Then we want to calculate the height from which the stone was dropped if the stone has a mass of 25 kilograms. So this is one of those ones where we go, right, what am I being asked about? This question is about energy. It's clearly about potential energy, and I'm being asked the height. So the height is unknown. I've been given the mass is equal to 0.25, and I've been given a graph that's got to do with potential energy. And if you write it down like this, it kind of triggers your your brain to go, right, I've seen this equation before. I've got EP, M and H, so this has got to be EP equals mgh. Now you can do the rearrangement straight away here, or you can use your triangle, or you can substitute, and it doesn't really matter. Oh, okay, sir, we can't hear. It's all broken. Why is that? That's a good question. Any better? Any better now? Yes? No? Good to know. Okay, it's just a bit echoey. Yeah, sorry. Maybe move it about a bit. Is that better? Better now? It's working. Cool. Maybe I'm talking too fast. Right, so potential energy equals mgh. So we stick our numbers in. We go to our graph. We know that the potential energy is 400. We've been told the mass is 0.25, and we've been told that we know that the gravitational field strength on Earth is 10 times h. So I'm going to do it by rearrangement after I put the numbers in. I just think it's a bit safer, but it's up to you. So that becomes 2.5 h. So we divide both sides by 2.5. So you grab your calculator on that one. You do 400 divided by 2.5, which is what? 40816. So h equals 16 meters. If anybody's got a calculator handy, just check that. I think that's right. I think that's right. Maybe not. 10 would be 25. No, that's not right. That's definitely not right. 160? Yeah, 160. Thought that was right. 160 meters up. Yeah, it's light stone. Drop from 160 meters. Okay, are we all good? Now the next question along here, state the kinetic energy of the stone after 2 seconds is here. And again, it makes use of that idea that the total energy remains constant. So if I'm at 2 seconds, which is not there, but it's here, I'm going to go and grab my little dotty line tool. From 2 seconds, dot our way up to our line and cut our way across. So after 2 seconds, I've got 300 joules of potential energy left. Okay, so my total was equal to 400. Oh, my timer's up. Just reminded me of that. So my total was 400. My potential energy, or EP, is equal to 300. So reasonably logically then, the rest of it has to be kinetic, so EK has to equal the remainder. So it's a simple takeaway. It's just 100, and it's worth 1 mark. Okay, so we'll finish off this stream by calculating the velocity of the stone after 2 seconds, and then I'll let you go back to your lives. So calculate the velocity of stone after 2 seconds. So that after 2 seconds, we know that the kinetic energy EK is equal to 100. And if you didn't work that out, by the way, in an exam, just make a number up, stick it in here, because you'll get an error carried forward. Okay, we know that the mass of the stone was equal to 0.25, and we're being asked for V equals question mark. Right, so this is our kinetic energy equation, left hand side, bottom equation. So EK equals 1/2 mv squared. So E kinetic equals 1/2 times 0.25 times V squared. And I'm going to wish I'd run my calculator app here, so if somebody in the chat can run ahead of me. So EK equals A half times 0.25 is 0.125 v squared. EK we can pop in, we know that's 100. Oop, subscripts are bad. V squared. Okay, so that gives me what, that 800 equals v squared. So we take the square root of both sides on that one, and we need the square root of 800. So v equals the square root of 800, and I'm hoping answers 12. Thank you so much, Sparky Extensions, you're a superstar. 28.3 to 1 decimal place meters per second. Alright, folks, this has kind of been a tech experiment as much as anything else. Thank you so much for 61 people turning up and tuning in. Really enjoyed this. So I will see you all tomorrow. Feedback is great. I'll leave the stream on for a couple more minutes. If you pop into chat what you thought, what I could have done better, what you'd like to see, kind of for revision sessions next, I'd really appreciate it. All right, thank you so much, everybody. Have a nice evening. Mic off. Rubber Flubber does indeed get a shout out for the amazing avatar. How many of my first year class was here? You're going to be amazing when you get the GCSE physics. Yeah, Irene, you get a shout out, okay?